And good afternoon, everybody. Let's get started with the class. For announcements, pre-lab and lab 7 will be done this week. So pre-lab due this Thursday, lab 7 on Friday. And that lab will be on diodes. And so we're going to continue talking about diodes today and rectifier circuits. So we'll get to some practical circuits for diodes. Homework 6 is due next week. So take a look at that for the date and time due. My office hours will be right after class if you'd like to join, talk about anything right after this lecture. So let's continue on with diodes by moving back to the whiteboard. So let's move back to the whiteboard here. So I started this example circuit with a diode. Remember that we talked about a diode, primarily what we're going to use it for, acts like a one-way valve or a check valve for electrical current. So it allows current to flow in one direction generally. And we talked about the real diode characteristic where we had a knee in a curve, and when the diode was forward biased, and a zero current flowing when the diode was reversed biased. And I introduced this diode approximation where we're going to say the diode is conducting current only when the diode voltage is equal to some V sub F forward voltage. That's about 0.7 volts for silicon. And the diode will not conduct when the diode voltage is less than VF. So we're going to use this diode assumption to solve this circuit. We have a voltage source that changes between different values, and we have a resistor in series with a diode. And what we would like to find is the current through the diode for these different source voltages, 5 volts, 0.3 volts, and minus 5 volts. So we're going to have to make an assumption about a diode in a circuit when we solve for whatever value we're looking for in that circuit. We're going to make the assumption that either the diode is conducting or the diode is not conducting. So let me write that up here so we can refer back to these assumptions. So we're going to assume the diode is conducting. All right, so we're going to assume the diode is conducting. So what does that mean for the diode to be conducting? That means, using this approximation, the diode voltage equals V sub F. Okay. And so when we make that assumption, we're going to check that assumption. We're going to check, so then check if ID is greater than 0. Okay, so I'm going to put a little cloud around this because we're going to refer back to this. Okay, so we're going to assume, well, this is one of the assumptions you could make, that the diode is conducting, and that means VD is equal to VF, and we're going to check if ID is greater than 0, which means current is flowing in the positive direction through the diode, not in the reverse direction. So we don't want a negative current when we assume the diode is conducting. That generally can't happen. Okay, so that's one assumption. Or, right, we're going to make the other assumption, which is assume the diode is not conducting. Okay, and so what does that mean? When a diode is not conducting, ID is equal to 0. And then we're going to check this assumption and check if VD is less than VF. Okay, so if we assume the diode is not conducting, then the diode voltage has to be less than VF, because if VD equals VF, we're going to assume the diode is conducting. And so what you can do is you can make an assumption based on what you know about diodes and what you can see about the circuit. You can maybe make a smart assumption, check it, and if that's right, then move on with your analysis. Or if the assumption is wrong, well, switch over to the other assumption and check that. Okay, so let's work this problem, this circuit, for Vs equals 5 volts. Okay, so we're going to find I1 for Vs equals 5 volts. Okay, so let's work this case. Just going to draw a line down here so I can fit a lot on this whiteboard. So for the case, where Vs equals 5 volts, let's make an assumption. So when I look at this circuit, and if I see that Vs is equal to 5 volts, I think there's going to be some way to have 0.7 volts across this diode. So I think that diode is going to be conducting, right? I think there's going to be a 5-volt voltage source here, probably some voltage across the resistor, which will let 0.7 volts be across the diode, and I think current is going to flow. But let me make the opposite assumption. Let's just see what happens if I make what will turn out to be the wrong assumption. Let's assume that the diode is not conducting. Okay, so we're going to make that assumption. The diode is not conducting. Sorry if that's small. I'll try to write bigger here. Okay, so what does that mean? That means the diode is not conducting. That means I'm going to assume I sub D equals 0. And then check is VD less than VF? Question mark. All right. Okay, so if I write a KVL equation, let's figure out what is VD based on a KVL equation. So let me start here at the bottom. I'm going to go to the left, minus Vs plus, well, what's the voltage across that resistor? That voltage would be, let's see, the voltage with this polarity, positive on the left, I times R would be I, so I1 times R1 with that polarity. So I can write a KVL equation that says minus Vs plus I1 R1 plus VD equals 0. Okay. And I'm trying to find VD, so let's solve for VD here. VD is equal to Vs minus I1 R1. Okay. So that would equal, in this case, Vs is 5 volts minus I1. We're assuming I1, well, I1 equals ID in this case, right? I1 is equal to ID. 0 times R1, doesn't matter what it is, it's 1,000 ohms, but it doesn't matter because this is equal to 5 volts. So I made this assumption that the diode was not conducting, and then I checked what is VD if there's no current flowing through the diode, and I found that VD would be equal to 5 volts. And we know that can't be the case. You can't be up here on the assumption plot, on the approximation, You can't be up here and have VD equal to 5 volts for a silicon diode. I should write that here, that VF, since this is silicon, oh, it's right here. VF is equal to 0.7 volts. So you can't have a VF of 0.7 volts and a VD of 5 volts and have current not flowing. Okay, so this assumption is the wrong assumption. Wrong assumption. Okay. All right. Well, then let's assume the diode is conducting instead. Figure out where that gets us. So let's assume diode is conducting. And so what does that mean? So if the diode is conducting, VD is equal to VF, line here, VD equals VF, and we want to check is ID greater than 0, question mark. Okay, so using this KVL equation, I can solve for I1, which is ID, right? ID equals I1 in this case. And so I can solve for I1. I1 is equal to VD minus, or VS minus VD over R1. VS minus VD over R1. Okay, and again, I1 equals ID. Write that up here. So this would equal 5 minus, now when you have current flowing through a diode, VD is equal to VF using this assumption, right? If I have current flowing through the diode, VD equals VF. So this would be 5 minus 0.7 over 1,000. R is 1,000. And so that would equal 4.3 milliamps. Okay. And since this current is positive, then I've checked, well, this assumption is correct. In other words, I can have VD equal to VF, and ID is positive 4.3 milliamps. So I'm somewhere up here, right? It's not negative, it's positive, that current. Okay. So this is the right assumption, right? Correct. Correct assumption. So the answer is, for find I1 equals 4.3 milliamps. Okay, so if VS equals 5 volts, I1 is 4.3 milliamps. Right? So let's work the case for, let's see, VS equals 0.3 volts. Let's do this. Let me draw a line here. So let's say VS equals 0.3 volts. Well, we will work that case. Now I think if VS is 0.3 volts, then there's no way I'm going to get 0.7 volts across the diode. There's no other source here. There's only a resistor. I don't think there's any way I'm going to get 0.7 volts VF across that diode. So I think that diode will not be conducting. But let's, just like we did before, make the opposite assumption. Let's assume that the diode is conducting and see what happens. Assume diode is conducting. Okay. And so that means VD is equal to VF. right? We're here on the curve. And we want to check, is ID greater than 0? Question mark. All right. Okay, well, we have an equation down here that calculates ID or I1, right? I1 equals ID from VS, VD, and R1. So we can say I1 or ID equals VS minus VD over R1, and that's equal to 0.3 is the source, 0.3 minus VD, right? VD is 0.7, right? Because this is a silicon diode over 1000. And that equals negative 0.4 milliamps minus 0.4 milliamps. So that can't be the case. You can't have VD equal VF. You can't have 0.7 volts across a diode and then have the current negative down here. That's not on the curve. That's not on our approximation curve here. So this is the wrong assumption. Right? So let's take the opposite assumption and see if that's right. So let's assume diode is not conducting. Okay. And so if the diode is not conducting, ID equals 0. ID equals 0. And then we're going to check, is VD less than VF? Question mark. All right, so let's go back here. Let's look at this KVL equation. VD is equal to VF. No, that's not right. That's not right. VT is equal to VS minus I1 R1, which is equal to 0.3 minus I1 is equal to ID, 0, times R1. So that's 0.3 volts. Okay, so on our plot here, you can see that you can have VD equal to 0.3 volts and have ID 0. You'd be somewhere like, here in the plot. So you can have 0 current and VD equal to 0.3. So this is the right assumption. This is the correct assumption. Okay, so the answer would be, so the question is, what is I1 for VS equal to 0.3 volts? The answer is 0. I1 would be 0 because ID is 0. All right. Finally, let's set VS equal to negative 5 volts. So VS is negative 5 volts. Current would try to flow counterclockwise around this circuit here. If this were just a resistor without a diode, current would try to flow counterclockwise. But that would mean that current is flowing in the reverse direction through this diode. Okay, this diode, I didn't label it D1 here. So I think that this diode will not be conducting. So let's make that assumption. Since we've made wrong assumptions, let's try to make the right assumption here. Assume diode is not conducting. Okay, so if the diode is not conducting, ID equals 0, and we check is VD less than VF. Okay, so let's use this KVL equation again. VD equals VS minus I1 R1, which is equal to -5 minus 0, and that's -5 volts. Okay, so that is the correct assumption, right? -5 volts here. Check, correct assumption. Because VD is less than VF. -5 is less than 0.7. So you're somewhere here. You're, go to the left to -5 volts, and you can have 0 current flowing. So that's how you can work these diode problems. If you have one diode in a circuit, you take a guess or make an educated guess or otherwise figure out if you think the diode is conducting or the diode is not conducting, and then check your assumption. If you have one diode in the circuit, you can take a guess. If you have two diodes in a circuit, then you have to take a guess for each diode. And you could probably figure this out once you start working with these circuits. You figure out diode number 1, oh, I think that is conducting, and diode number 2, I think that's not conducting, and then you can check your assumptions. Okay. And in the worst case, you pick first 3 times out of the 4 possible combinations you choose wrong, and then you have to work it out to the end to get the final check of both assumptions are correct. Okay, for the 2 diodes. All right. So that is generally how you will work the textbook problems or the homework problems. Make the assumption, check the assumption, and get the answer. Next, I want to show you a couple practical circuits using diodes that are pretty common. Okay, and these circuits are called rectifier circuits. So rectifier circuits, they generally do this. They convert AC to DC. Okay. So what that means is you have an AC source. Okay, so this would be, I'll just draw a schematic or a little plot here. You have an AC source where this is some voltage versus time. And what you would like is to put something in the middle here between the source and the load so that you get a DC voltage there or close to a DC voltage. And that circuit in between is called the rectifier. So there are a couple kinds that we're going to talk about. One is called the half-wave rectifier, and the other is called the full-wave rectifier. So let's talk about the half-wave rectifier. Okay, and let's use a sinusoidal source, Vs of t. And let's say it's 10 sine omega t. I'm using sine instead of cosine just because it's easier to draw in this case for me. So there's my sine omega t source. And then I have a load over here. Let's make that load a resistor. Okay, so this is R sub L. And there's some voltage V sub L of T across that resistor. Okay. And in between, this is going to be the rectifier. Okay. So let's build this up incrementally. Let's say I put a diode here and make that connection at the bottom. I'm going to add another component here, so leave some room here if you're drawing this. And let's say this is diode D1, and D1 is a silicon diode, which means you can assume in this class that the forward voltage is equal to 0.7 volts. And we'll make that a diode approximation that we used on the last problem. Let's create a plot of Vs versus time versus time, and VL versus time. And then just see what happens here. Okay, so the source is a sinusoid, sine wave. And let's draw this out here like this. Approximately. Okay, so something like that. And so let's talk about what's going to happen here. We saw in the last problem that when you have a series resistor and a diode, that no current is going to flow until the source, that voltage source, equals to or is equal to or exceeds 0.7 volts in this case for the silicon diode. So we're going to have no current flowing through this resistor until that source equals 0.7 volts. So if I say this is 0.7 volts here, and come down, then I have no current, so I have no voltage. This is V sub L. Right, I have no voltage, so VL is 0 until the source voltage equals 0.7 volts. And then this source voltage is going to increase until it peaks out at 10 volts. Right. And as soon as the source voltage exceeds 0.7, you get some current flowing. Okay. And while current is flowing, the diode voltage VD is going to be 0.7 volts according to our approximation. So the remaining voltage is going to be across the resistor. So we're going to see this sine wave sort of appear across the resistor, look like this. Okay, it's supposed to be about the same shape. And then when the source voltage falls back to 0.7, you get no current again, right? And so if you have 10 volts across the source and you do a quick mental KVL equation here, you have 0.7 across the diode, you'll have 9.3 across the load. And then the source voltage goes below 0.7 and it goes negative. And we know from the last problem that when we have a voltage less than 0.7 volts, you get zero current. So there's going to be, by Ohm's law, 0 volts across the resistor, right? Until you get another pulse here of current through the resistor. So it's gonna look like this. Oops. Something like that. Okay. And then again over here. Right? So something like that. Well, we've not really created DC because DC, remember, for DC voltage, the voltage is constant and it maintains its polarity. Polarity does not switch. Well, polarity doesn't switch here, but this is far from constant. So what I'm going to do is add another component here. I'm going to put a capacitor here. Okay, so that's a capacitor. And so what happens is this. Current flows once the voltage Vs exceeds 0.7 volts. Current flows through that diode. It's flowing through the resistor, but it's also charging that capacitor. The voltage across that capacitor equals the voltage across the resistor. Okay, so that voltage increases across the capacitor and the resistor until this peaks out here. And then what happens is the source voltage falls. So it starts falling, right? Source voltage starts falling, but that capacitor has a charge on it. And the charge from that capacitor, once this voltage VL starts falling, can discharge and cause current. That capacitor discharges and causes current to flow through the resistor. Current cannot flow backwards through the diode. Current can flow out of the capacitor through the resistor. And one of your homework problems when we were talking about RC circuits was, well, what does that voltage look like across the resistor and across the capacitor when you have a charged capacitor discharging its energy into the resistor? And the answer was, it looks exponential. So, and that exponential curve depends on the time constant. So you get this exponential decay. You hit another charging cycle of that capacitor when the voltage at the source increases, right? So it comes up, and then you get this repeatedly. Well, that doesn't look very DC either. It looks like a repeating sort of sinusoidal rise and exponential fall here. But what we can do is take this capacitor and make it big, right? So the time constant of this R, L, and this C for this shape here might be, I don't know, out here, 5 tau might be out here somewhere. So the time constant might be something like that. But what if you take that C and you make it bigger? You're essentially going to move 5 tau way off the whiteboard here. And so if I use a bigger capacitor, I might get that, right? And if I use a really big capacitor, I make it something like that, just a little exponential decay there, right? And before it has a chance to decrease significantly, I hit one of these charging half cycles and the whole thing happens again, right? So this is starting to look like right here, DC. It looks fairly constant. We do have a little droop right here, but you can make this droop as small as you want by increasing that capacitor. So let's say this is 9.3 volts and you only want that to fall zero point 0.1 volts or 0.01 volts. You could design a capacitor value such that this exponential fall only falls whatever voltage you want. Okay. And so there's going to be some ripple on this output DC voltage here, but that ripple might only be, 0.1 volts, 10 millivolts, 5 millivolts, whatever you want it to be. So it's approximately DC. Okay. So that is a way you can use a diode and a capacitor in a rectifier circuit to convert a sinusoid into DC. And so you could charge a battery, you can run a DC electronics device, whatever you want here, um, using this approach. All right. So that is the half wave rectifier. That is one way to convert AC to DC. Let me next show you the full wave rectifier. So I'm going to erase this if there are no questions on this. I don't see any in the chat, so I will continue on to the full wave rectifier. Okay, let me draw. Let's see. Someone asked in the chat, if I add a diode in parallel with an inductor in series as the rectifier, would it work out the same? Diode in parallel with an inductor in series. Let's talk about that at office hours. I want to understand your circuit. If you're describing a better way to filter the voltage across the load, then maybe yes. But I want to try to understand your question there. So let's draw that out in office hours if you could stick around for that. Okay, so let me draw the rectifier first here. We love to draw these with diagonal diodes. You don't have to, but we do. Okay, so that's the rectifier, sometimes called a bridge rectifier or a full wave rectifier. On the left, we're going to put the source. And let's make this again 10 sine omega t. And on the right, I'm going to move this out just a little bit because you can probably guess we're going to wind up putting a capacitor here. It's a resistor. It's the load voltage. I have some R sub L here. All right, so let's talk about how this works. I'm going to draw this graph again of VS. Let's try to fit it up here. VS and VL. So this is VS of T. This is VL T. And VS of T is going to look like a sine wave. Something like that. Okay, let's talk about the possible ways you could have current flow through this rectifier, through this whole circuit, really. So first, for the positive half cycle, when VS is positive, current is trying to flow out of the positive terminal of the source into the negative terminal of the source, as shown here. And so current's trying to flow this way. Current gets to this junction here, and it cannot flow backward in the reverse direction through this diode, but it can flow forward through this diode, right? Gets to this point, it cannot flow backward through that diode. Remember, it's trying to get back to the negative side of the reference polarity of this source, right? So it cannot flow backward here, get back to the source, but it can flow this way, like that, through the load, this way, up here. Remember, so there's no connection here. This is a hop over, one wire over another. Gets to this junction here. And so it looks like it could flow either way through these two diodes, but remember, it's flowing to a point of lower potential. This would be a point of higher potential. So the current is going to flow this way, right, to make it back to the negative reference polarity here. So that's the flow of current from the source, through the rectifier, through the load, back to the source. For the negative half cycle, when the voltage goes negative, current is trying to flow out of the negative reference polarity of the source, the voltage is negative, and into the positive reference polarity of the source. Okay, so let's trace this out. Current's trying to flow this way, gets to this junction. It can't flow in the reverse direction through that diode, so it flows this way. It can't flow in the reverse direction through that diode. It can flow this way. It goes down through the source. Right, up to this point. It looks like it could flow either way, the forward direction through the diode, but it's trying to get back to the positive side here, which is really the negative side because the voltage is negative. Right, so it comes this way, that way, and back to the source. Okay. Someone asks, does that mean we don't, let's see, does that mean we don't even need that diode where the top is higher? No, actually you do, you do need all of these diodes because, like, for example, this diode here had to block the red current, the red direction, and this diode has to block the blue direction. So you do need all of these, and we can trace through that. Okay, so the big thing to notice here is that positive charge flow current in both cases where the cycle is either half cycle is either positive or the half cycle is negative, for both of those cases, the current flows down through this resistor. And so what that looks like on this plot is this. Now, in the red direction, the positive direction, notice that the red current flows through two diodes, this diode and this diode. Each of those diodes, I didn't write it here, but let's assume they're silicon. So the diodes are silicon, and VF equals 0.7 volts. I had to cross two diodes, so that means I have 1.4 volts of drop between the source and the load. Okay, so if you run the KVL, you'll see that I have to overcome 1.4 volts here. So this is 1.4. And this is also 1.4 here. And I get this pulse. This peaks out at 10 volts. And 10 volts minus 1.4 is 8.6. So this is 8.6 volts here, right, at the peak. Okay, so that's what the load voltage looks like for the positive half cycle. Now the same thing's going to happen here, where this is minus 1.4 volts. Okay. You get that horrible sine wave drawing, but you know, that's what you get. And so that current flows through that diode until the source voltage reaches negative 1.4 volts, and then it crosses positive, and the same thing happens. Right, so we get this. So we get pulse, 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 like that. Okay, so that doesn't look very DC, right? But if you take a capacitor, put a capacitor right there in the rectifier, right? Then that capacitor is going to charge up, right? It has the same voltage that the resistor has across it. And when the source voltage falls, you get this exponential decay. Okay. See, someone asks, is the 1.4 just two of the diodes? Yes, 2 times 0.7. And the 8.6 comes from 10, right? The peak source voltage minus 1.4, which is 2 times 0.7. That's why this peaks out at 10 here. Take away two diode voltages and you get 8.6. Okay. Now, so this doesn't look very DC either. Looks a little ripply, but you could take this capacitor and make it larger and make this ripple basically as small as you want. You have a physically larger capacitor, that's a trade there. But then you could reduce this ripple down to 0.1 volts, 10 millivolts, whatever you want, by having a large enough capacitor. And you've taken AC and converted that AC source to a DC load voltage. Okay. All right. So why do this? Why use 4 diodes instead of 1 diode? Well, you can use a smaller capacitor, right? Because you have a shorter time between the cycles, between the charging cycles of that capacitor, okay, or the charging half cycles. So you can use a smaller capacitor. And someone asks, can you make a capacitor have a value that's too large? Yeah, physically they get bigger. They get more expensive. They have different frequency characteristics if you're trying to do this with higher frequencies. So there are trades. There are trades for when you make the capacitor larger. So, okay. So how do you do this, right? What if you have house power? How does this work for when you have 120 volts AC? You know, you might have seen power supplies that use this approach. So let me just write here, 120 volts AC. Okay, you know that's a sinusoid from what we talked about. Well, what you can do is, and we're not going to talk about these, but you can take a transformer. A transformer transforms one voltage to another. It's inductors wrapped around usually some kind of common core. And if you have a 10 to 1 turns ratio, 10 turns for every 1 turn like this, then if you have 12 or 120 volts on this side, RMS, you'll have 12 volts on this side. You get a step down. And then you could put your rectifier here. Let's call that your rectifier. And then you could have your DC load over here. So you can take your house power, AC power, step that down, have a rectifier, and then a DC load. Okay. All right. So I've hit the wall on time for today. So in closing, check out the pre-lab. It is posted. You'll do lab 7 this week. Homework 6 is due next week. There will be an exam next week. Take a look at the schedule. I will talk about that during the next class, and we'll send out an announcement about that. But we'll talk about that later. So thanks for joining class. If you'd like to join office hours, just stick around. If not, I'll see you next time. Have a great night.